SwayamPrabha. Digital India. Educated India.
Good afternoon, everyone. So we will start our lecture today. Basically, we'll be working on stability analysis. However, in the last lecture, we performed stability analysis for a parabolic equation. Today, we will perform stability analysis for elliptic and hyperbolic equations. Now, before we start today's lessons, we'll make a comment on last lecture. We'll take up last but fourth slide from the last lecture. If you recall, we were trying to find out amplification factor, and that we arrived at equation 8 from the governing equation after substituting the error quantities, and in equation 8 we substituted cos theta equal to e to the power minus I theta plus e to the power minus I theta by 2. So this is the identity e to the power I theta plus e to the power minus I theta by 2 makes it cos theta. We substitute cos theta in equation 8 and we get this equation in terms of e to the power at, which is effectively the amplification. Then cos theta minus 1, this is substituted by minus 2 sine squared theta by 2, and we get equation 9. And finally, we find out condition for which modulus of e to the power at is less than or equal to 1. And finally, from there, our conclusion is that the stability requirement of one-dimensional parabolic equation is alpha delta t by delta x square less than equal to half. This alpha is thermal diffusivity. In case of momentum transport, it will be molecular diffusivity or viscosity. We'll take it up later, but right now, as an example, we took up one-dimensional heat conduction equation, and we also discussed two-dimensional heat conduction equation, which is also parabolic equation. And for that, we found out alpha delta t by delta x square plus alpha delta t by delta y square less than equal to half. So this was the conclusion of our last lecture. Now we will take up second order wave equation. Here c is the wave speed and u is the wave amplitude. This can be written also as a system of two first order equations. If we substitute v equal to del u del t, and if we bring in a function w equal to c into del u by del x, then it is possible to write del v del t equal to c del w del x or del W del T equal to C del V del X. It is same. Now if we can write that, then possibly from there we can form a first order equation which is del U del T plus A del U del X equal to 0, where U is now, U means an array of V and W, and A means a matrix 0 minus C 0. These are the elements. So this equation, second order wave equation, can be represented as a system of first order equations. And then we can find out eigenvalues from the matrix, which is lambda, and simple ways to find out determinant A minus lambda I equal to 0. This I, of course, unit matrix, not unit complex number. One has to be a little careful. And so lambda square minus C square equal to 0. We get two roots, lambda 1 equal to plus C and lambda 2 equal to minus C, representing two traveling waves with the speed. One is del X del T plus C, another is del X del T minus C. These can also be called, this del X del T1 and del X del T2, this can also be called characteristic lines for the wave equation. One is from here, if we find out, one will be X equal to Ct, left running, passes through a point left from the point of interest. If I is a point of interest, delta X left I minus 1. So X equal to Ct runs through I minus 1, and X equal to minus Ct, this runs through I plus 1 point. We'll show this graphically in one of the slides, subsequent slides. So I minus 1, I plus 1 are separated by delta X. Now we are talking about system of equations. Now system of equation in this example is hyperbolic, and it has also been seen that the eigenvalues of the A matrix represent the characteristics differential representation of wave equation. Now Euler's equation may be treated as a system of first order wave equations. For Euler's equations in 2 dimensions, we can write a system of first order equations as del uppercase C T by del T plus A matrix del E del X plus B matrix del E del Y equal to S, where E is an array U and V, E means U and V, A is a matrix, elements are U0 0 U, B is another matrix, elements are V0 0 V, and S is a source term in Euler's equation, which are basically pressure gradients, minus 1 by rho del P del X and minus 1 by rho del P del Y. So Euler's equation in 2-dimensional Euler equations can be represented as system of first order equations. Now first order wave equation, if we consider, we can write del U del T plus C del U del X equal to 0. Now del U del X, if we go for finite difference equivalent, del U del X we can write as U I plus 1 n minus U I minus 1 n by twice delta X. This is second order accurate. Second order accurate derivative of the first order term. first order derivative is expressed through second order accuracy. Then del u del t, this can be expressed as ui n plus 1 and minus ui at nth level. This I at nth level is taken at nth level but average between two neighboring points, I plus 1 and I minus 1. So ui plus 1 plus ui minus 1 by 2 is ui, and that is at nth level divided by delta t. Then if we feed in del u del t here and del u del x here, we will get an expression for ui n plus 1, which will be simply, as you can see, ui plus 1 plus ui minus 1 at nth level by 2 minus c delta t by delta x, ui plus 1 at nth level minus ui minus 1 at nth level by 2. We are giving a number. These numbers are arbitrarily problem specific. I am not maintaining number for all the slides in a sequence. So this particular problem, this is equation 1. And the time derivative, the way we expressed it was first done by Peter Lax, and it is called Lax method. Famous mathematician Peter Lax developed it. There was a purpose we'll come to know later in subsequent lessons. So once again, having done that, we define our error at any arbitrary element m. So as you know, it's a Fourier series. Any arbitrary element of a Fourier series has been taken, which is epsilon m, equal to basically e to the power at, e to the power unit complex number I km x. As done previously, we substitute equation 2 in equation 1. That means in this equation the error quantity, because if u is substituted by d plus error, then this equation is valid, and then this equation is valid in d also. So if we subtract that, we get an equation in error, and there we substitute error quantity, and just the way we did it in case of parabolic equation, again we will get an expression for e to the power at cos km delta x minus I c sin km delta x. This c has been formed by clubbing together c delta t and x. So the c delta t and x, this combination has been substituted by uppercase C, and we get this expression. And all of us know that stability requirement is modulus of this, that means e to the power at, that means modulus of cos theta minus I c sin theta, where theta is km delta x, has to be less than or equal to 1. Now modulus of this is basically cos square theta plus sin square c square sin square theta. From there, and root over that quantity basically. So from the root over cos square theta plus c square sin square theta. From there, we try to get the simplification done. We will see that in order to satisfy the condition for the amplitude be less than 1, we have to have c less than equal to 1. That means small c delta t by delta x less than equal to 1. Uppercase c or less than equal to 1, or lowercase c delta t by delta x less than equal to 1. This uppercase c is called Courant number. This equation restricts actually delta t. If this c delta t by delta x has to be less than 1, it poses a condition on delta t. That means delta t has to be less than delta x by c. And that will make this solution of this equation stable. If we choose delta t less than delta x by c. That is the stability requirement. So equation 3 is called Courant, Friedrichs and Levy condition. In my introductory lecture, I mentioned about these three scientists and their enormous contribution on partial differential equations. And this condition is called CFL condition, that Courant number is less than equal to 1. And I was mentioning about xt plane, left running characteristics line, right running characteristics line, through one is through I minus 1, another is through I plus 1. You can see for unit Courant number, this is basically delta x by c. Our delta t for the 1D wave equation has to be less than that. So this is the the limitation. We have to, the numerical space has to be less than the analytical expression of delta t equal to delta x by c. So Courant-Friedrich-Levy condition is based on Courant number, where Courant number is c. Here it is wave velocity delta t by delta x, where c is the wave velocity, delta t is the time step, delta x is the spatial step. For one-dimensional first-order hyperbolic equation, CFL condition obtained by the above procedure is c less than 1. Different stability conditions for different equations can be obtained from appropriate conditions, and then by substituting c, because everywhere velocity plays a role, so restriction on velocity over a time step, that is obtained from this CFL condition. And if we substitute in the stability requirement expression, combination of c delta t by delta x or velocity into delta t by delta x, we'll get uppercase c, or basically Courant number. Now we will take up another very popular transport equation. As I said, that we will take all the all possible equations. That means we have taken parabolic, we have just discussed about hyperbolic, and now let us discuss elliptic equation. And I have chosen vorticity transport equation. I am sure all of you know what is vorticity transport equation. If the x momentum equation is differentiated with respect to y, and y momentum equation is differentiated with respect to x, and then former is subtracted from the latter, we get basically vorticity transport equation. So this is, as you can see, omega is del v del x minus del u del y. So that quantity omega, lowercase omega, which is vorticity into dimension given by del v del x minus del u del y, that quantity is transported in this way: del omega del t plus u del omega del x plus v del omega del y equal to nu, coefficient of viscosity, del 2 omega del x2 plus del 2 omega del y2. And again we apply FTCS, that means forward in time and central in space. The time derivative del omega del t has been discretized: omega at ij point, omega ij at n plus 1th level minus omega ij at nth level by delta t forward in time minus u. Here u, the velocity, will act as coefficient. V will act as coefficient. This is how we get rid of nonlinearity. And then omega is discretized by central difference: omega I plus 1j minus omega I minus 1j divided by twice delta x, omega at nth level. Then again omega j plus 1 minus ij plus 1 minus omega I j minus 1 by twice delta y. Omega has been written as nth level. Then nu into central difference of omega in x direction at nth level. Again plus nu into central difference of omega in y direction at nth level. So all the spatial variables are discretized through central differencing scheme and temporal term discretized through forward difference scheme. And we have just, this is another problem, yet another problem. The first problem we handled today was wave equation, which is hyperbolic equation. This is elliptic equation. So we have started giving new numbers. So this is 1, this is 2, and then again usual von Neumann analysis. The error quantity has to be substituted by a Fourier series and exponent in time domain, and then take up any representative any representative number, any representative expression from the Fourier series. So here we have taken mth quantity, or e to the power I kmx plus I kmy. This is an e to the power at. This is basically the representative term of the error quantity. This is substituted again in equation 3, and then you have to do little bit of algebra here after substitution, so that you can get an expression in epsilon ij n plus 1th level divided by epsilon ij nth level. Sorry, I have been mentioning this e to the power at e to the power I km delta kmx plus e to the power I kmx. This is error quantity epsilon. So epsilon is substituted in the governing equation, and then through some algebraic steps we will get epsilon ij n plus 1 divided by epsilon ij at nth level. That means this is amplification, is e to the power a t plus delta t e to the power I km x plus y divided by e to the power delta t e to the power I km x plus y, and which is basically e to the power delta t or this amplification factor. And then if again, as I said, after substitution, if we do little algebraic calculations, we'll be able to express g. We did it in detail while doing it for parabolic equation. Here we are just similar steps have to be followed. We will get 2 dx plus dy plus 2 dx cos km delta x, 2 dy cos km delta y, minus I, imaginary part, is cx sin km delta x plus cy sin km delta y. And here delta x or delta y's, we can see delta x is nu delta t by delta x squared, dx is nu delta x by delta y squared, dy is nu delta t by delta y squared, and cx is u into delta t by delta x, cy is v into delta t by delta y. And again, modulus of g has to be less than equal to 1. This will then pose condition which is modulus of 1 minus 2 dx plus dy plus 2 dx cos km delta x plus 2 dy cos km delta y plus this imaginary quantity. Entire expression under modulus operation or modulus sign has to be less than equal to 1. If we apply that, we will get these two conditions: dx plus dy less than equal to half, cx plus cy less than equal to 1. Now dx equal to, if we say dy, because difference between dx and dy only the grid size. This is grid size delta x in x direction, this is grid size in y direction. So if we take equal grid, then we can substitute delta x and delta y by delta, and that if we write that as d has to be then less than equal to half, less than equal to 1/4, which means nu delta t by whatever is the grid size, it is same in now x and y direction, grid size squared is less than equal to 1/4. This is twice as restrictive as the one-dimensional diffusion limitation. Again, the spatial case, we can say the velocity in u direction, x direction and y direction, if we assume that those are same, and again delta x equal to delta y, then it is possible to write cx equal to cy equal to c, and if cx equal to cy, then we can see this is less than equal to half. So this CFL condition is also twice as restrictive as one-dimensional case. So diffusion limitation is twice as restrictive as one-dimensional case in 2 dimension, and CFL condition is also twice as restrictive as the one-dimensional equivalent, one-dimensional case. So now we will go for stability analysis of second order wave equation. We will not go to construct a system of first order wave equations. Rather, we will solve second order wave equation, which is del 2u del t2 equal to c squared del 2u del x2. Here we, since this is central difference, this is second order derivative, we are substituting this with a finite difference quotient, which is central difference. So ui at n plus 1 minus twice ui at n plus ui at n minus 1, 3 time levels, divided by delta x square equal to c square, then del 2u del x2. Again we apply central differencing between I plus 1 and I minus 1 point in between I. So all are at nth level, divided by delta x square. Then again, if this n is the solution of this equation, then equation 5 is satisfied by n. If u is replaced by n, then if n is replaced by d plus e, d is the ideal solution of the finite difference equation without any rounding of error, which is physically not possible. When we get a solution from machine, from computer, this rounded up error has to be there, rounding error. So d plus e epsilon. So we substitute d plus epsilon, then this equation holds good for d. We subtract equation in d from equation in d plus epsilon, we get an equation for error in terms of epsilon. And then again epsilon is substituted by any term of Fourier series, which is e to the power at into e to the power I km x. Now that means basically 6 and 7 substituted in 5, and then again we do some algebraic operation and we get this equation: e to the power a delta t minus 2 plus e to the power minus a delta t equal to c square e to the power, this is unit complex number, I kmx plus e to the power minus I kmx minus 2. And c is Courant number, which, while doing the algebraic operation, we have clubbed together c delta t and delta x in this way, and that is capital C. So we will get from here e to the power delta t plus e to the power minus a delta t equal to, we just have transferred 2 on the right hand side and then substituted e to the power I theta plus e to the power minus I theta by cos theta, then cos theta minus 1 has been substituted by minus 2 sine squared theta by 2, and we have gotten this term, this equation, which is equation 9. And again the amplification factor is epsilon at ith location n plus 1th level divided by epsilon at ith location at nth level, modulus of this is the amplification factor. So we can write modulus of e to the power at, and that should be less than equal to 1. Now if we rearrange equation 9, we'll be able to get this quadratic equation, equation 10. Just rearrange this equation, divide by e to the power e to the power minus a delta t, and we will get this. So this is equation 10. This equation 10 can have will obviously, quadratic equation will have two roots. One root, if it is greater than 1, then stability condition will not be satisfied. So both the roots have to be equal to 1. That is only possible if it's a complex root. If it is a real root, it's not possible. So it has to be a complex root. So complex root means this discriminant should be less than 0. So arising out of this, we will have to find out the condition. So you have written everything here in details, that e to the power at is the magnification, e to the power a delta t is the magnification factor. If its value exceeds 1, the error will grow exponentially, which will lead to an unstable situation. All these possibilities mean that equation 10 should possess complex roots in order to both have the value of e to the power at equal to unity. This implies that discriminant of this equation has to be less than 0, has to be negative in order to get a complex root. So it is simple algebra. We can clearly see, in order to satisfy this condition, that 1 minus 2 c square sine square km delta x by 2 whole square minus 1 less than equal to 0, sine square value is always positive, and from there we can get that c square has to be less than 1 by sine square km delta x by 2. So, which is always true if c is less than 1. Hence, CFL condition, which is Courant number less than 1, again must be satisfied for stability of second order hyperbolic equations. So we have seen parabolic equation for which restrictions were posed on the coefficient of diffusion, time step, and the grid size. Then we have seen first order wave equation where condition was Courant number less than 1. Then we have seen elliptic equation where conditions are posed both on diffusive term and Courant number. And now we have obtained the stability condition for second order wave equation where Courant number is less than 1. So from the calculations it is clear that numerical instability arises. If numerical instability arises, solution becomes unbounded. We never want that. In actual fluid modeling problem, stability restriction are applied locally throughout the mesh, grid mesh, and minimum is obtained that is used for the entire problem, that is used for the entire algorithm that is applied to solve the problem. Now, one thing here, the stability analysis which we have done on linearized equation. Even just slowly I will go to vorticity transport equation, which is definitely a nonlinear equation, but if you recall, I mentioned u and v's are considered here as coefficients, which makes the equation linear. So these are linearized version of the nonlinear equations. So von Neumann stability analysis is a linear stability analysis. So hence delta T obtained from such analysis cannot be directly used when we will be solving full Navier-Stokes equations or Euler's equations or energy equation, if any nonlinearity there in energy equation. Of course, energy equation is usually the way we solve is, again, it's a quasi-linear equation. We find out velocity field first and then feed the velocity field in the energy equation to solve for temperatures. Whatever it is, we will discuss when we will take up those specific problems. What I want to mean that basically fluid flow problems are nonlinear problems. So this stability analysis, whatever delta T we get, cannot be directly applied to it. Just the value that we are guided by, the condition that we get from the von Neumann analysis. But this is definitely helpful because this gives us the indication. Actually, having obtained this indication from the stability analysis, we have to take delta T little less than the restrictive value, and then we have to try it for the entire problem. And this is sort of numerical experiment. So we have to set up a trial run, 2-3 trial runs to see whether delta T is functioning well. One may argue that if we go for implicit formulation, we don't need that. That is true. But when I mentioned it earlier, when we want to capture exact transient, especially for turbulent flow problems, when we calculate for direct numerical simulation or large eddy simulation kind of scenario, every time step, intermediate time step is meaningful, then we cannot avoid this explicit advancement rule. And there are a few other problems also. Some, heat conduction problem where transient is very important. So, wherever we have to proceed through explicit formulation, stability analysis is of paramount interest and paramount importance. So we have to go through stability analysis to decide on the time step. We have seen earlier also that in order to increase the accuracy, we have to make the grids finer. But not only making grid finer will raise the formal order of accuracy, you have to go also for higher order schemes. But higher order schemes we cannot go arbitrarily. We have to obey always the consistency related restrictions. Having done that, we can go for higher order discretization method. Then we can apply very fine grid size, as fine as possible for a given computer. But then it will eventually impose restriction on time step. You have seen that time step is related to spatial grid size, delta x or delta y in 3D, delta z. And that is why stability, knowing about stability, understanding stability, and being guided by the stability requirement is essential to have a stable and correct calculation. We'll stop here today. We'll take up remaining issues related to discretization, finite difference formulation and other associated problems in the next class. Thank you very much.